never mind quickly where we stopped last time. So we're dealing with one covered by two charts with closing sets of logic, satisfy this relation and intersection, and CP1 is acted upon by L.2. So there is a map from substitute the global vector fields, and of course gives rise to the map of the universe one belonging to the global, to the algebra of global differential operators. A quick computation showed that the center, positive degree center goes to 0, and so this map factors through the quotient. And the result I finished discussing last time was that this last map is not small. I call this a theorem for arithmetical reasons, because this result will find its analog for vertical. But in reality, this is a very important lemma, essentially, needed for the proof of the following truth, so to say, fundamental theorem that is given the name of actually Bernstein Davidson localization, which says that the L2 function. So if we start, so consider two categories. The category of D modules. Oh, this is a. So I guess I have to say a couple of words for students. What do I mean by that? So of course, if I don't know A is an associative algebra, then we'll know what the category of A module is. If it's a shape of associative algebras, and sometimes in speech you just forget about the word shapes of algebra. Sometimes you mean shape of algebras, as is the case here. So if this is a shape, then we know what an A module is. So it's a shift that is acted naturally by the shift of algebras A. So they want me to say, what does it mean to have a shift somewhere? So it means that for any open set, shift M is a rule that, first and foremost, is a rule that to each U attaches M of U. Since we have an A, we also have A of U attached. So M of U must be an A of U module. And then there are some axioms of this one. I assume you know them. And if you don't cook them up, it's straightforward. So we, in this particular case, we have the category of D modules. So this whole theory is about the comparison, as we have already seen, between geometry and the representation theory. So we have the category of G modules. So this obvious map here means that there is a functor, gamma. Fundamental algebraic geometry functor that to a D module attaches the space of a global set. Because of this, it is automatically a G module. the functor is there is also a functor in the opposite direction called localization. That send curly M to what can we do? You can take M, you can take the shift D, you can tensor one by another over SL2. What this means is that we identify elements like this. So if P is a differential operator and G is an element of SL2 or envelope, you can freely move it from left to right. So if you have a G, then you regard it as an element of this algebra, so you have Chiral G, and this is the same as P tensor G applied to M, except we're dealing with a G model. So this, of course, obviously a G module. The name localization is an obvious origin. That's how, at the beginning of the study of algebraic geometry, people define all modules over a fine schemes. Remember that. So a module over an affine scheme is the same thing as a module over the space of globally defined functions. And you go from this, the module over this algebra of globally defined functions to a shift in this way, except that D must be replaced by an L, N to me. So the fundamental theorem is that these functors are inverse of each other, parts and category theory, if that is what it means. So the categories are equivalent by means of the functors. So to a large extent, this famous theorem, even in this particular...
You 0G
Of course.
Still.
Of course. Thank you.
So you mean
It's then, yeah, then G of... I apologize. So, I guess U of SO2 0. So, even this particular case, the point, of course, that the theorem is valid for any simple algebra. And in this particular case, that we will see, it gives interesting examples. And to a large extent, a theorem like that is a justification for introducing, actually studying the module. Of course, the most important result here is that this theory was used to prove the famous Kazan-Lusztig conjecture. Of course, I will say nothing about that. Let's look at examples. It will be a source of some exercises for the beginners. And then we will move on. So examples will be concerned with concrete such maps between concrete such objects. So what is the simplest possible G module? A trivial one, of course. So what's the localization of the trivial module? Can you guess? I mean, question to those who have never thought about it. So, what are we looking for? For a module, for a sheaf, whatever else it is, for a sheaf on CPU1 whose space of global section, see these are inverses, the space of global section must be C. I told you everything. What's an actual such shift? Never covered. This is structure shift, of course. Why is that? Well, just by the definition, it's a Lisian computation. So we'll write dCp1 tensor over SL2. Let's see. SL2 generates even the entire space of global section. But remember, this is all over function, so there is no doubt that, and an exercise is to think about it and prove all the statements I'm making here quickly. That, of course, is the same as quotienting by the right ideal generated by vector fields. But remember our discussion of differential operators is generated by vector fields. The graded is the symmetric algebra, so everything that's left is of degree 0, and degree 0 is a full functions. You could go backwards, of course, and see easily that gamma of will be all right. A more interesting assumption. G lives there by means of vector fields. So you can to get an SL2 module, you can simply pick your favorite open subset and consider the space of all function sets. The group moves open subset, and so an open subset may not be fixed under the action, but infinitesimally, an open subset is fixed, and therefore Lie algebra automatically acts on the functions on any open subset. Which one shall we choose? So we have CP1 and we have this suspicious point, infinity. Infinity is, of course, in terms of, well, it's a matter of choice. So if the 0 of one of the 2 points, say y equals. I gave you last time formulas that give the action, and those use the x. So I think that those formulas are in our world, and now we place ourselves elsewhere. Infinity. So you can consider the space of sections of structure shift on CP1 without infinity. That, of course, is just C, one of the charts. Now, of course, this is the space of global sections of a shift that is easy to cook. For example, you can denote it as the structure shift. The structure shift is the shift of functions that are irregular. But suppose we allow poles of arbitrary degree at infinity. I will use this notation. I'm not sure it's a standard notation. So what I mean really is that this is a shift of functions that are allowed to have poles at infinity. Never mind whether or not infinity belongs to your open subset. That makes sense. It's the same thing as the standard. So if we have R at map my C into CP1, then what's written here is the same thing as this usual direct image of the structure shift of C. But that's what it is, really. So, as a vector space, of course, it's but the space of polynomials in a different variable. In X. So, it has a basis, 1, x, x squared, etc. Agreed? Any questions? This looks like a chain. People familiar with some representation theory of SL2 know that typical representation of SL2 also looks like a chain. You have, for example, a highest weight vector, and then elements would be something like the highest weight vector, and then say F moving like this and P moving like this. This is a typical picture of an highest weight SL2 module. And it does look like this. And we know that this must be an SL2 module. What is it? So, exercise. Verify that this C of x is naturally isomorphic to the contragradient Verma module with highest weight. So let me remind what is exertion. So for any complex number in U, I can define an SL2 module M of don't have to do it by the way, maybe everybody knows. Okay, thank you. Getting some answers. Delightful. So, formally it's an induced representation from one-dimensional labeled by my U from the what's called B, so the Lie algebra spanned by H and E to the whole thing. In terms of the universal enveloping, you take U of SL2 and you quotient out by the left ideal. Quotient by the left ideal, you get left module. Generated by two elements, E and H minus 2. So the picture I started making somewhere, this or that. So from this definition, it immediately follows that 1 as an element of the universal envelope, or rather, it's class.
Y2.
Hmm?
Y2.
Y2. Oh, no reason for so 1. It's cubed by E, and this condition ensures that it is multiplied by U by H. And Poincaré-Borchert theorem will tell you that the whole thing looks like 1 and then F1 and F squared 1, etc. So this is the picture I alluded to a few moments ago. F acts like this, and E up some coefficient will act like this. That's Verma. I claimed we get not a Verma module, but a contragradient. So this whole thing is graded. Here are the graded spaces. The whole thing goes in layers. So you take the U. But you take the U in a the U dimensional space is huge. I just want to direct some of the U's to components. So by this I mean the direct sum of graded components. H will act on these components as follows. Mu on 1, at the next level it will be mu minus 2, verified u minus 4, etc. It's because H gradient f is minus 2. So u minus 2 times n. It's a standard thing that the algebras automatically acts on the U to a module, and in this particular case it will act on this restricted. Unfortunately, that's not the thing, because if you do this, then you will have a module that goes in the opposite direction, so it will change the signs of the vector spaces. I want to stick to modules, I think, living in this way. And for that, the action is given by E goes to, should be entered the module. So F, H to H, and F to E. To make it this right. And then F. So pull back. But, so F still F there, as I explained, but E will act as F, not as E. All right, so finally the statement has been made. The actual computation is easy. You just remember we discussed this. E acts as minus ddx, H as plus sign, so something like this. So you just write the formulas and see if it works or not. Another, so we will have three nice modules associated with this situation. We've discussed two. Finally, the most interesting one. A module that's supported, so next, example 3. So this module is supported on infinity. So what you do is you take the t and you quotient out the ideal of that point. It's clear what I mean. So technically, I probably figured written d of CP1, mod out d of CP1, and then the ideal of infinity. So this is a module, so we have CP1, we have infinity, and this is a module that is automatically a zero outside, but on a subset, on any open subset containing that point, it's given by something like this. So what's the result? Think about it. You pick the neighborhood that's another C. So to say spec of the algebra of polynomials in Y. We know perfectly well what D looks like over the set. It will be expressions involving Y and d dy. But Y is filled. So as a vector space, this will be something that has 1, dy, dy squared, etc. d dy acts in the obvious way, but you will compute how x acts. For example, x into 1. Y dy is what? We know that y kills 1, so we want to move it. We do, and y kills 1, so that's 0, but we have to pay the price. It's not a commutative algebra, so minus 1. So that's the structure. So it's a typical example of a D model. So the space of such things is what is the way we algebraists think about distribution supported at the point. So these are, you think of one as the delta function. This is the derivative of the delta function, etc. That's an algebraic model of such things. For this reason, I will even denote this module as delta, just for future reference. Delta sitting with infinity. Right, that's how we manipulate if we have to take a function analysis course with delta functions. We know that we can differentiate them, but it is killed by the function that vanishes at that point. So that's what we get. So, but be it as it may, delta is n SL2 much. Just as any D module is. What is it? Exercise. So the space of sections of which really is the space of polynomials in U1, informally speaking, is the Borman module. The Borman module that of the highest weight minus 2. People who know something about the L.2 representation theory will notice that what highest weight 0 modules, such as the contragradient Borman, and highest weight minus 2 modules have in common is that the Casimir element, the center acts by 0. And so this makes sense because we know from our result that the center character must be the 0. Does all of this give us something? Yes, it does, and that's perhaps where I will finish this discussion. So, imagine for a second that we know nothing of the representation theory of SL2.
Sorry, what do you mean by OSL2 model? Ah, this is the answer. Sorry, sorry. I understand. Sorry.
No, that.
Sorry. Thank you.
Common sense immediately tells one that there is an exact sequence of sheaves. Actual of D modules. I will show you that these are, it's the D module that we've just considered. So what is it that we have? We have the sheaf of functions that are allowed to have a pole at infinity. Of course, it has a subsheaf of functions that are regular. And that's part of it, so that's the beginning. And then there is a quotient. What do you think the quotient is? It's on the board, a hint. Oh my, how many O modules are there on the board? Delta. Why is that? Just think about it. So, outside of infinity, these two fellows are equal to each other. So, in what way this is different from that? It's bigger in that we allow poles at infinity, but if infinity is not part of your set, there is no difference. So, outside of infinity, they are equal. So, we have to compare them sitting at infinity. Sitting at infinity, this thing is Laurent polynomials. And that thing is, of course, just polynomials. So it's how they teach us to call it in complex analysis. It's the space of singular parts, principal parts of holomorphic function. So it's, it's as a vector space, it's all things that are forced to have a pole. The regular things are forced to be, are killed. Now, of course, this thing is a D module and behaves exactly the way our delta does. You see, so there is a 1 there, or rather, the class of 1, an element in this algebra. And of course, it's killed by, no, 1 is not there, I apologize. 1 is here, why inverse? So there is, so to say, the alleged by inverse, or rather, its class. And of course, y kills it, just because y makes it regular, and that's 0. On the other hand, dx, they're completely free. We apply d to y inverse, you will have minus y minus 2. And you see immediately that d will generate from y to the minus 1, the whole thing, absolutely free, no relation. That, of course, is that thing. You would perhaps agree that this is just common sense. But now let's use the Valence and Bernstein. So y is a function of global sections. And all of a sudden, computation of the global sections of each of these shifts we've just accomplished. This is an equivalence of categories, so this function is exact. And therefore it makes an exact sequence into an exact sequence. And what's the result? Well, that's C. That's the contragradient of our volume. And that's, as we discussed, very much. Who has seen a picture like that? That's the famous BGG resolution. It's a essential result of representation theory of the old category, obtained more or less for free from geometry. So, this, of course, it's a toy example, but it really gives you a feeling as to how this geometry helps in your algebraic questions of representations. Any questions? So now I'll move on to the important topic, what this introduction, this discussion of ordinary stuff, not vertical stuff, was intended for. But before I do that, I'll motivate the next step. So if we are to find this interesting, then immediately the question arises: can we? Of course, C is a very simple but can we get something less simple? So, what's the localization of a generic finite dimensional homology? That cannot be achieved in exactly this way, just because its central character is different. It has some quadratic expression in M1. So, but we already have a hint. So, remember we discussed that CPN or CP1 carries, so O comes from O, but there are other shapes such as O hat. And naturally, there's perhaps they both theory. It's known that the spaces of global sections are exactly L.2. So, if we are to do this for a module like this, we would like to interpret ON as a D-module. It cannot be literally a D-module as we discussed. In order to consider it, be able to consider it as a D-module, we have to introduce twisted algebras of differential operators, or algebras of twisted differential operators, whichever way you. I don't know why you grabbed 4 boards and then, after all have been used, it doesn't make sense to switch them. So twisted differential operators. To give you a hint, I will start with an example. And exactly the example I've just considered. It's an example of the following obvious general picture. So X is a smooth variety. L X is rather, I wanted to say L is a space of sections of rank 1, vector 1. We like working with sheets of sections of 1. So I will say that L is a invertible sheet, isn't it? So rank 1. Oh, that's not. Then you can consider D sub L. So we want this to be the subalgebra of C-linear transformations of I probably have that right formally. So what I want to say is we are looking at transformations defined locally so that in terms of the local coordinate they are given by differential operators. So transformation of L locally given by differential operators. I'm deliberately being vague. I don't want to be very careful, and I actually expect that students here will think about this carefully and make all of this exactly correct. But of course, locally, if you fix a small enough set, you can identify any such shift as a shift of functions locally over for any point over sufficiently small u. And so locally, there is no difference between dl and what we call dx, which in that terminology is simply d sub ox. But transition functions can be different, and that's the point. So just as I said, exercise. I'll think about it and give the relevant definitions. Honestly, see that this is a sheet, etc. I will, instead of doing this somewhat boring job, I will show you an example. In fact, this is not an example. Now I will do an example. So let me consider the above mentioned OM on R. So again, we have x, y, x equals y inverse over intersection, and the space of the module is trivial over the corresponding two copies of C. And the module is trivial over each, and so it has the generator S0 there and S1 here, and the meaning of that is that, say, S0 equals y to the n S1. You get the structure shift precisely when n is 0, and then both S0 and S1 are identified and thought of as unit. So what's d over n that? Well, on each of the charts, it's still the familiar DC. Global sections are what sometimes is called the Weyl algebra. X ddx or y dd. Now let's see what ddx looks like in terms of what? So in order to see that, what is it that we have to compute? So I want to apply dx to S1. It makes perfect sense. After all, dx is defined on that other open set. It's y squared dy. But we can compute it independently, so we don't really need the something that be defined there with log O. So actually, this makes sense on the intersection. So in terms of y, it means on the intersection of the two charts. And so we expect the result to be a rational function. Can we compute it? Certainly. Dx is what? S1 is, well, S1 is x to the n. It's x to the n. What's the other way around? It's y to the minus x to the n. Yeah, by the way, when I write the dx, what do I mean? I mean the element. Sorry. Locally, we know that the algebra is just a differential operator. So it means that locally, dx is the thing, by definition, is the thing that thinks of S0 as the unit. So this is 0. So the action of the dx of one section of this sheaf are evaluated as if these were just sections of the structure sheaf. What shall we get there? Well, we first have to rewrite it like this. And then use that formula. We will have x to the n minus 1. That's not. Now back to S1. N x n minus 1, and this not is y to the n S1. Almost all of this goes out. X steals y, and so what remains is n times y S1. So what this computation showed is that ddx in terms of y is, if it were just functions, it would be y squared dy, perhaps to the minus. And then there is a correction. I wish I had correction, very important. That's what we will be dealing with from now on. So there is a correction. The unit is no longer killed. So we need to add n y. And you see, just as I promised, locally there is no difference. But this is a transition form. There is different from the standard one. It contains a part of the standard one, but it has a correction. And that's what happens in general. So you are advised to think about it and convince yourself that you will always be getting something like this. All right, so what does it tell me about the sheaf of differential operators operating on the sheaf? So, what does this look like? Now, recall that the usual, so to say, DO is 0, was generated by the functions and the cotangent. We dealt with the following exact sequence. Which actually splits. And the whole thing was an appropriate version of the universal envelope. So that we discussed. Now in this case, we also have this. The algebra is automatically filtered. Again, think about it. It's filtered for the same reason, by definition, as the usual algebra of differential operators. So it has the degree 1 component. And the degree 1 component, of course, define it, if you like, in a way, in an invariant way. It contains, of course, the structure shift. Why is that? Well, of course, multiplication by functions is a differential operator. The differential operator for the theorem commutes with multiplication by function. All of this works for any L. And the quotient is automatically CP1. That's an indication of it. So the quotient here would be getting about that. Now, what that formula shows is that in this particular case, this doesn't split. Probably doesn't prove it, but it's easy to prove. And that this term is a very strong indication of the fact that this sequence doesn't split. But otherwise, we expect the whole story to be the same. The whole algebra will be generated by these things, more or less, by definition. Continue with this example exercise. Find the embedding of SL2 into the space of global sections D1 OM. Once found, it will make ON a sheaf of SL2 modules and the space of global sections, the SL2 module that we were hoping to localize. That makes sense? All right. So this example, of course, prompts the desire to similarly introduce and study a more general class of such algebras called algebras of twisted differential operators. Let's do that. I may have mentioned this already, and if not, then I will say it now. So all these lectures is about the study of such kind of exact sequences. And for vortex algebras, we will get a similar. And the whole point is to explain what meaning these three objects have in the vortex world. So how is this done in general? So first of all, we need some terminology. So what are the formal properties of sheet like this or like that? So the first notion here is, again, we have an A, and from now on, A will always be small. Meaning, as you remember, that omega sub A is. So L is called M A R B A algebraic. The vertex algebra there will be the chiral algebraic. Yeah. So L comprises the following data. L is an A module. Of the algebra. also make it precise, but it's not an A-Lie algebra. The Lie bracket is not A-linear, but it's the linearity is violated in a rather precise manner. So these further two properties will be about that. So the next structure piece is what's known the anchor map. A morphic of the algebras and a module. I will call it denoted sigma from L to T sub A. So this third piece of data allows me explicitly describe in what way the bracket fails to be A-linear. So the bracket of, I will typically write psi for an element of an algebra, and A or something like this, a Latin letter for an element of A. So a bracket like that is given by the Leibniz rule, and you are interested how psi acts on A. Well, this sigma. So sigma makes psi into the vector field of derivation, and just like A. Eta plus, of course, A, the bracket of psi in A. Do such things exist? Certainly. The simplest possible example is A itself. Of course, sigma is oftentimes called the anchor map. So it's such, and sigma is just the identity. So the point of this discussion is that we're trying to describe D1 like this as a Lie algebroid. But it's a Lie algebroid of a special kind. It's different from T sub A, but not much, only by A itself. So this situation is the subject of the next. So all the terminology, I think it's due to understand balance with that. That's where I and people I know learn. Maybe there is a better way. I don't know. So maybe Lie, perhaps also A. Algebroid is a Lie algebroid L such that the anchor fits into the following exact sequence. So we have so that informally speaking, the arrows with respect to the structure. I think more specifically, I guess, what is there to discuss? So sigma is a morphism of the A algebraic, so that's part of that definition. So A as well as L is an A module, so this is a morphism of L module. Notice that now we have L operating on itself as a Lie algebra via the joint action. And A then automatically is the ideal with respect to this Lie structure. Agreed? So L automatically, a joint action can be restricted to A. So L operates on A. And this is the last condition. So L operates on A via the anchor. So psi, the bracket of psi with A, I'm going to write a formula that definitely looks tautological, it's not quite tautological. It's tautological in the case of T sub A. There, indeed, these are elements of an associative algebra, we can bracket them. Here, this is a bracket defined on L. A is an element of A, so it's an ideal, and therefore it's closed on the action of A. And so the question is, what does this equal? And the answer is, you take psi, you apply the anchor, you get derivation, and you evaluate. So this simply carefully axiomatizes what we have seen here. So this thing automatically is a P-curve.
So your map A to L is part of the structure data or canonic?
Yeah, Yongzhang, it's terrifying to speak to you, see everything. That's a subtlety. Let me think. You understand the way there is a logical subtlety. Do I require that there is a map like this, or do I say that this map is part of the structure? And I think it's the latter. So it's not the existence. So what is it that I know? It exists. So you wasted all this time to torture me. Where is it? So it's a Lie algebra. Yeah, you plus a map like this, so that thing, this thing is exact. So that's agreed. All right. I think this is maybe it's still somewhat less than half of the time. But on the other hand, I gave you the definition. Yeah. Let's make a break and then we will discuss classification.
How much time do you need for a break?
Last time we agreed that it be 15 minutes. If you want to change it.
No, I don't want to change it. 15 minutes.
15 minutes.
I made a decision. And the question is right. What is a G-log? Of course, there is a trivial example. The one that we've seen all along, where you know what I'm talking about. That what happens in the standard ring of differential operators. So this map is projection onto A, and A here is, you know, identity 0, and the bracket is the standard. A plus psi, B plus eta, is psi eta plus psi of B minus eta of eta. So I will sometimes refer to this as the standard. Chiral here. What else is there? That's the question. In order to answer it, we need to introduce the category. So, more. So suppose we have two such things. What is a morphism? That, of course, is an illustration of Jules' remark. A morphism is a map from L1 to L2, map of that preserves the map that preserves all the structure of an A module, the structure of a Lie algebra, and also such that it makes this diagram commute. So let me, do you know that I'm going to curve the key out? The category of such things. Clearly, any such morphism is an isomorph. Very simple exercise. So this is a group of. All right, so we have one object there. Let's try to hook up as many as possible such objects. So remember, A is 3, so we can write L equals the direct sum. So it splits over A. The sequence doesn't split the sequence of the algebroid, but does split the sequence of A model. So you can always do it correctly. And this space carries a standard structure of the Chiral algebroid. So standard. What else is? If you think a little bit about it, you will realize that the only room for maneuver there is as follows. So we want to hook up a new bracket. Bracket any elements taken from different components, or if at least one of them is A, this is all fixed. Just look at those definitions. A is abelian, TAF on A in a prescribed manner. No choice there. But the bracket of these, the room for maneuver is limited, but non-end. Modulo A, it must be at best. That's also part of the structure. But maybe another function will pop up. So any bracket must be like this. So alpha is a function of the variable. that's the best we can say about it without thinking. Much more can be said very quickly. Some of you perhaps already see it, even those that have encountered such things. So this must be a Lie bracket. So anti-symmetry implies that alpha is anti-symmetric. Next, Jacobi. You know what? I should have started differently. Jacobi is the most interesting. Here is another simple observation. Both are emojis. This is going to be enabling linear thing. L must be A by linear. This is also obvious. Have I erased this? The bracket itself is not A linear, but it is not, the A linearity fails in a prescribed once and for all manner. It fails via the anchor map, and this map preserves the anchor map. So whatever you vary must be A linear. So think about it. I think my explaining it will only confuse the matter. So think about it. It's obvious. But just now back to this thing. So Jacobi is the most interesting part of this whole discussion. So let me clear the board for that. So let me compute tau psi theta. So I started computing. So there will be an alter. Then tau hitting this will produce me 1 over alpha tau psi theta. Or tau will operate on alpha. I'll write it like this, but it actually is a bracket. I just think it's a vector field tau applied to this function. So the same as the bracket, just writing like this makes it more economical. Make sense? That's an A function and that's a derivation. So if you think of this as a vector field, I apply this vector field to this function. So you get the Jacobi by adding the cyclic permutations. This is what happens. It's so first of all, cyclic permutations of this will all give me 0 due to this being a bracket. What do the 6 terms coming from 2 cyclic permutations of these to remind you of? Look, alpha is an anti-symmetric and A linear. So such things comprise, altogether they give us the space of what? 2/4. The result is an expression involving functions of triples of vector fields. And anybody with any knowledge of differential geometry will see that this very much resembles the co-boundary of alpha. So what's written here is, by definition, that the round differential applied to alpha evaluated on tau psi eta. So let me remind you for those who forgot what it means. So associated to any ring, especially when it's smooth, there is the round constant. 0 forms, 1 forms, 2 forms, etc. So these are n linear over a and asymmetric. And the formula for the differential, for example, here, is one of the standard things in differential geometry. So if I have a function of two variables, forget about this alpha, this is an arbitrary alpha. So alpha is a function of two variables. G alpha will be a function of 3. And the formula is, if you don't know this formula, an a priori formula, then you should write what's written here and you will obtain the definition. But of course, the formula is this. What you have to do is you make a choice. And of course, all of this is a morass of signs. There would be some more overall sign. I forgot what it is. But then the signs flash. You take out one of those, and as you go from one to another, the sign changes. And then there will be 3 more terms, and again, up to a sign. So what you can do is, you don't take out anything, but rather you pick a pair to bracket, say tau and psi. And then you consider the remaining two such pairs. You don't, the thing is anti-symmetric, so it doesn't make any sense to swap them. You consider two different pairs, so you preserve the order. And at each point, at the end, you change the sign. So, eta. And this makes it a complex for the reason that the square is 0. In principle, such a complex can be written for any Lie algebra. In this particular case, we are dealing with the Lie algebra of derivations. And in such case, we require that these forms or cochains are alinear. But if you forget about an A-module structure, you observe that this formula makes perfect sense for an arbitrary Lie algebra, and you simply have no grounds for any extra condition like linearity, and then it makes gives you the famous Chiral cohomology complex, the Lie algebra. And in any case, write carefully these formulas using anti-symmetry, and nothing else is to be used. And you will see that, so whatever you get, believe me, is precisely the formula for the Duran co-boundary of L. So, conclusion. Are there any questions? This is really important. I've probably told you a lot of rubbish today, but this is something that really is important for what follows. So here is this important conclusion. for each alpha. So we introduce so introduce in addition to omega 2 such a space of closed to the set of those that are closed. Introduce the space of closed to form. So what we've accomplished is for each closed to form, we have attached a Picardly algebroid. In this notation, L of 0 would be the standard. A plus sub A. So, and any Picardly algebroid is isomorphic to an algebroid of this.
Why?
Why what?
I mean, this last statement, I don't understand. What we have seen is that this acts on that, I mean, that we have an action of the closed forms on PL.
Yes.
But I mean, to start with, you have to know that it splits as modules.
It does, because I said it was this, A is smooth. So it's a
But still, this does not imply that. Yeah, look, so A is affine, so that's an affine situation. So that's not.
it's a free TA is a free A module.
Okay, so geometrically speaking, we are in an affine situation. That's
Even
not
more
it's
than
not-
that.
it's
Even
not-
more than that. And I'm not sure that on a smooth affine variety the space of
No, of course. I mean, we have the freeness,
Yeah.
but also the affineness. So on
Yeah.
so on a like P1, we have additional phenomena. Like,
No, I'm just talking A is fixed.
Okay.
I'm not talking about
Yeah, sorry.
No, that's what I said. Oh, yeah, well, PL sub A. Perhaps this. Yeah, so A has been fixed constant. I'll tell you what happened on the variety. All right. So what are the motifs? Some of them may be isomorphic, even if the alphas are different. So let's talk about morphisms. So we have one such thing. And another. For each, so when I write it like this, what I mean is that for each I have fixed this decomposition. This is something that may change, and morphisms will change this. So I fix that, and then the bracket is expressed via alpha, as I explained above. So what does it mean to have a map from here to there? Well, just look at that definition. This definition. Where the room for maneuver is. An element of A goes to itself. An element of T goes to itself modulo A. So the most that we can have is an alleged vector field goes to itself plus some function. Well, you change splitting, you will change this function, but that's all there is. And now a similar discussion. What if alpha 1 and alpha 2 are fixed, what beta should be, and in general, what do we expect from beta? For the same reason as above, beta must be alinear. For the same reason, nonlinearity is fixed once and for all. It's only q to the n time. So whatever we vary must be alinear. Otherwise, we just have to see what a change like this does to a bracket. So let me call this map. Beta must be, of course, A1. So let me compute phi sub beta of psi, phi sub beta of beta. And the bracket with respect to my right like this. So just, you will see in a second what it means. So the rest is an exercise. I probably could have simply formulated the result. So, all right, let me state the result and do this computation. And if I get confused, the fault will be all mine. But at least here is the result. Phi beta is a map, and automatically an isomorphism from L alpha 1 to L alpha 2 if and only if, can you guess? Up to sign. We will see. So the difference between these two shifts, we'll figure out the sign in a second, is, yeah, of course, the differential of beta. So 1/4, we get another. We should get the difference of 2. So why is it? So I have, probably for safety, I should leave this computation out as an exercise. But let me, that really is fundamental. Let me show you. So what is it that I want to verify? I want to verify that phi beta of psi, phi beta of eta, alpha 2. I have to compare it with phi beta of the alpha 1 and see whether or not this equals this. Right? If it is, then we get a morphism. Make sense? So this is my question. When does this equal this? This one is easier. That's content of the definition. So this thing goes to psi eta plus alpha 1 of, yes, psi eta. So it's, I just wrote what that is. So I apply phi to this thing. Phi leaves fixed function, but this thing goes to beta of the bracket. Agreed? How about that? That's a little more involved. So psi plus beta psi. Eta plus beta eta. You probably start seeing that this is the round differential. So Yeah, that's L.2. So the bracket of these two will give me this. The remaining brackets are completely predetermined. So psi beta minus eta beta psi. And so when we compare these to cancel out, and we see that the difference between this and this is indeed an expression involving three terms of the type psi beta eta minus eta beta psi. If I move it on that side, then minus beta psi beta. That exactly after assign the standard formula for the Chiral differential of beta, as promised. So an exercise, of course, here, figure out all the sides. All right, so we have these two conclusions. Have I read one? So any object is like objects up to isomorphic are labeled by three forms, by two forms, and two such objects are isomorphic if and only if the difference is the co-boundary of a one. So that's the fundamental result. It is convenient to give it the following refined form. I'll just use this as an occasion to use some fancy terminology. So the defined form of all of this. So I will introduce I think I will denote like this omega 1, 2. So the category such that the objects are two forms closed and the morphisms from one to another is immediately gets the one forms such that the difference is so the category close to forms, morphism between close to forms, or one forms whose differential equals the difference. Something like so. This thing, I'm sorry to say this, is an abelian group in categories. So this thing is an abelian group I will not be defining such thing, but it's such a nice example and simple and explicit that I will simply show you the structure pieces and then probably nothing else really is needed. So what it means is, so what do we have in an abelian group? A set and an addition. What do we have here? Instead of a set, we have a category. An addition is, we have a function. So bifunctor, actually. But we think that the bifunctor assigns to a pair of objects like this. The sum, of course. You can easily verify that this is a indeed bifunctor from the definition, quite obvious, and that you can figure out what associativity means, the commutativity, and all such things. Of course, carefully doing this is so painful, it's quite obvious. There it is. You swap two terms, you of course get the same thing, etc. All right, so what does this result mean? I'm not telling you anything in this, so I'm just reformulating it in a pleasing form, that's all. So, our results about PL means an action, they use capital letters to signify that this is an action of a category rather than a group, of a group in categories rather than a group. That is to say, functor, bifunctor. That a pair alpha L sends to L. I'm slightly cheating here. There is a bit of a gap. Think about it. So I'm saying that for any object, even if its presentation as L of alpha is not fixed, this operation makes sense. So the result is canonically independent of its choice, because it's an addition, doesn't matter. If you like, it's a shift. So you shift by 2, in our Newtonian universe, shift by 2 is the same wherever you begin. That's the concept of. And again, there is associative just because you add alpha. So think about it. Why is this an action? So you have to consider the compositions, compute them in different ways, and see that the results are canonically identified. So,
what's the error of alpha?
Well, alpha 1 plus. That's what I mean. If L was L of alpha 1, then of alpha it would be L of alpha 1 plus alpha. What I was trying to convey was the statement that if you change representation, then the result is canonically the same. That's what I'm saying. That doesn't describe the entire discussion here. It only explains that we can add an alpha. But remember, there was a statement that any object is isomorphic to 1, and the two are isomorphic precisely when the difference is a closed form. So there is an action. In addition to that, we have the following. So fix, I don't know, some fix alpha naught, or fix an object like this along the delta node. The following is true. The function that defined by alpha goes to this has been alpha not plus alpha. It's clearly a functor. Is an equivalence of categories. I haven't told you anything new. I'm just showing you how, using these big words, you can give a nice form to the discussion about. That's what we proved, haven't we? So the two objects here are equivalent if and only if the difference between two forms there is exact. That's what it says. Nothing else. No more, no less. In particular, the set of isomorphism classes of Chiral algebroids is, you see that, of course, simply the rank homology. Meaning, of course, take the closed two forms and quotient out the exact. All right, so this is just, as you mentioned, it's a fixed local situation that we gave ourselves. That's how we think about this. We have a variety, we fixed a point, we fixed a sufficiently small open set, and we described Chiral algebroid there. Now, let's describe sheaves of such. So let's try reading all of this. And then smooth. Variety. So what there is in the most, so we start with, Chiral algebroid on X, Chiral algebroid is a shift. Just replace A with the structure shift, T of A with the shift of vector fields. And so it's a shift of all modules and blah, blah, blah. So just like the Chiral, so essentially Chiral all X algebroid. It says it all. And of course, just as above, we have the category of those, and morphisms are maps that make the diagram commutative. So all of this makes perfect sense, absolutely automatic. in fact, if you forget the origin of Picard-Lie algebroid, the very fact that there is one such sheaf on a manifold is not obvious. So the reason that there is such sheaf is, well, it's obvious. Yeah, well, of course, you have O of X and T of X, shift T of X and operates on OX. So yes, there is one such thing. But if you just had this description given more axiomatically, then perhaps for some reason you could see that such things can be defined locally, but you may wonder whether or not one globally defines such things. And this is exactly the situation that we will encounter with algebras of Chiral differential operators. And so just by way of preparation to those things, pretend that the situation is more complicated like this. What we have is a shift of categories of Picard the algebroid. By this I mean that I'm not saying anything of content. I'm more or less repeating myself. So here is a manifold. Of course, what we know is that if we pick a small enough set, so to say, max set of OS, then we will describe such things inside. And so we will say that for any set, not of this, we have a category of Picard-Lie algebroid, so sheaves there such that their restriction at any point to a sufficiently small open set is as we described it. I'm not writing anything, I just don't know what to write. It's kind of abstract nonsense. You agree? So if you fix such set, so you have a category for this set. If you fix a bigger set, you have a category of such things for a bigger set. And there is a functor from a bigger to smaller, the restriction. These are sheaves, so for any object, a sheaf on a bigger thing, you get an object of this category living here, simply by using the restriction. So all of this simply to say that obviously there is a such category. Furthermore, our classification, again, I'm not saying anything new, just that's what the definition means. Definitions mean. So the terminology is such that such sheaves are said to be bound by the complex. It's just a terminology. What complex? The truncated the round complex I just introduced. Omega 1. Omega 2 close X. So it's truncated on both sides the round complex. But the meaning of this phrase again is just repetition of what we've done for many. It's more or less a tautological thing. And so locally, yes, saying that it's bound by this complex is simply to say that if you fix small enough U, then objects will be omega 1 to torso, just as I said. Things like that. So there is such a thing for any manifold. All right? So the question arises, how many such objects are there? It's a question similar to the previous one, it's different. But now I give you my third program, CP1. We will discuss the case of CP1 soon. It's given an X. How many objects are there? There is at least one. the standard of x plus q of x, the standard one. It's just the replacement of the standard a plus t sub a before. There is at least one, definitely. How many more are there? Oh, of course, better to say what is the set of isomorphism classes of objects. Now, having probably wasted some time on something tautological, let's again try to enjoy ourselves, because this is going to be, again, absolutely explicit and instructive. Constructing objects. So we'll try to do something like I did previously on this part of the course. So constructing objects. So what have we done locally? Well, we had a standard one, and then we did something to get to the rest of it. Likewise here, I will start with a standard one. How can I get a new one from this? Well, I'll have to tear it apart first. So I will consider UI a cover, an open cover, so that, as before, omega x of I is here is one such U. Have a standard one here to get all mu ones defined locally. I replace I replace the standard one only on UI. As we discussed. Oh, let me change the notation slightly. Oh, 0. That's the standard. L standard is the same as L0, just a matter of notation. So I will add an L5. So we know what to do for each UI. At each UI I attach the close to. That will give me a shift on the smallest, on the subset. I do it for all UIs, and in particular some other UJ. So this is on R, and on UJ I likewise have L2. Now I need to discuss the intersections. If I'm to get a global shift, I should be able to glue them on the intersection. So alpha L alpha I restricted to the intersection is isomorphic to the other guy. If and only if there is a beta ij and one such that dbij equals alpha j minus alpha I. So, is that all? No, that gives me, such beta is not unique. It gives me a way to glue things over the intersection. To get an honest shift, I have to verify transitivity. So now we have to, so I've got this identification. Now I need the transitivity. So on each UI, uj UK, I should have, you know what, going from I to J and K, and then back to I should give me the same, or going from I to K directly or through J should give me the same result. So what it means is something like the condition, you can guess, I'm sure, that something like this. IJK minus beta IK plus beta IJ equals 0. So rather beta IK equals beta IJ plus beta JK. So that's exactly what I said. All right. Now, of course, you probably already start seeing what is happening. We've got, in other words, a bar context. Well, if we don't, so there are two directions. The drum and the check.
Excuse me.
Yes.
If is equal to 0, is it not closed?
Yes?
Not closed. Just equal to 0.
Equals to 0. That's the map. That's the actual map. Alpha must be closed. And the difference of alpha must be exact. But that's an actual map. An actual map must be equal to 1. Two maps must be equal. So they are equal to 0 on the nodes. So we have a biconvex. In one direction we have the drum convex. We only need two groups, and I will shift them. So at 0, 0, sitting at 0, 0 will be 1 forms. Will be 1. Sitting at 1 will be 2 forms. Close to 4. In the check direction, so on this horizontal line, we will have forms living on an individual cell in direct sum of them. Here I will have 1 forms living on intersections. And here 2 forms living on intersections. So what we have just computed is as follows. In order to get a globally defined shift, different perhaps from the standard one, we need for each UI a collection of closed 1 forms. So in terms of the check, a 0 check co-cycle with values in closed 2 forms. Closed means that the drum differential sends it to 0. This expression here, alpha I minus alpha j, or the other way around, living on intersections. So the bunch of such expressions is the first check co-cycle with values in closed 2 forms. So this thing is the value of the check differential on that 0 check cosine. So this doesn't have to be 0, but living here is the bunch of beta ij 1 forms, and the theorem of which equals the corresponding value of so the round here. All signs have to be straightened out. That's straightforward. Let me not even try to do that, because if I do it carefully, I'll certainly fail. But figure it out if you like, if you're not, when you're not disturbed at all. And finally, each of those, this last condition, it means that the Chiral differential of this thing is 0. This, of course, simply to say that the bunch of two forms sitting here and one form sitting there is the cochain in the total complex. So H such shape is given by I don't know, by an element of, so look at the degrees. I shifted the round degree by 1. So this is the space of one cochains in the total complex. Of this bicomplex, typically stated by X, and check complex on X with values in the complex. It's just a matter of notation. How do we know such thing? So this thing reminds you that we're dealing not with an individual shape, but with a complex of shapes. And since this is a sheaf on a manifold, you can compute its check cohomology. And so this is the total complex I'm talking about. And the simple computation simply says that any shift is determined by the first coefficient. Correct? It's a general property. I haven't given you this. I just use these words, perhaps trying to navigate later on if you encounter hard to read modern papers in so it's a general property of gerbs bound by a complex. It's always like this. This is a concrete situation when I computed it for you, but it's always like this. The objects, if you have objects are labeled by first co-cycles of a total complex, like that. Some of them may be isomorphic. Can you guess what the set of isomorphic classes is? Of course, if you have exercise the set of isomorphic classes of such shapes is simply Z1 mod out Z1. So simply the first total homology of X with values basically truncated. The wrong complex. But the reason is, let me say a few words. Why is that? And let me figure out the actual difference. So look, we've created a new object by putting something here and something there. So let's go chain co-cycle conditions hold. Can this be isomorphic to where we started? Well, of course. Adding alpha I may give you nothing new if alpha I is a boundary of something. So, in order to kill this, you put something here. And if you can do so in such a way that this is the differential of something new, then at least these are filled. Are you done? No, of course. This identifies things locally, but now you have to see what happens as far as the transition functions go. And this is taken care of by this differential. So, if you have an object such that you can put something here so that its total differential is this object, so now both play a role, then it's isomorphic to the standard. And so the result then will be, think about it, this is all within common sense. Any questions so far? Let's look at examples. We really have one series example, CP1. So return to CP1. What does all this machinery give us on CP1? So we are after the first cohomology with coefficients in the thing. Any simplification that's, I know, it's so late. It's so easy to, lecture. It's so hard to listen. I sympathize with you. But let's try to just finish it like that. Do you see all the simplifications of what I've written here in the case of CP1? One group is 0. You see which one? This one. The dimension is 1. So that's 0. Therefore, this is the same, or rather for this reason, this is the same as omega 1 closed. It doesn't, yeah, well, I'll mention it later. At the moment, it doesn't really matter. So we are, therefore, after computing the first cohomology with coefficients in one form. Now that's a nice, it's known to an exercise. So CP1. It's C plus C, so this is our cover. And the intersection that enters this game is, of course, C star. So the exercise is, in this case, this thing is one-dimensional, and a typical representative is the logarithmic form, ddx on x. Verify this. This is very easy. Now remember, we had an example. D1 ON. Well, we had this example. Let's forget for a moment about this example. Let's try. Let me show you what all this prolonged discussion means in this particular case. You remember what one form on the intersection means. That's the transition function. That's the transition function. So it means that it gives you a shift that's locally the usual one, but gluing is twisted by the one form. So ddx goes to itself plus ddx on x, evaluated on dx. The claim is this is so this you see this is so dx goes to ddx plus 1 on x. So it means that d1 O1 that we discussed, or minus 1, is precisely the one that's produced by my form. Why is that? This computation occurred in a different form. I went from x to y. In terms of y, this is minus y squared dy. That's what I obtained. Dx went to minus y squared oy. And then there was either plus or minus y, and that's exactly what it is, because 1 on x is y. So up to a sign ddx on x gives you this shift. It's just a comparison of two computations. Yeah, something wrong?
Oh,
Seriously. It's clear. Am I making myself clear? Really? If I was able to explain something, this is it. So if you don't get it, then I fail completely. All right, so to get an arbitrary such thing, you will need plus or minus n times n ddx on x. And in principle, it's a general. It's the general situation. So for an arbitrary L over an arbitrary x, you get dl. Remember, this part has to do with varying things locally. DDL local is the standard thing. So more generally, you will be getting things like that by picking 0 for omega 2. But if so, and this becomes non-trivial condition in general, here omega 1 is automatically omega 1 allowed. But in general, if this representative of the cochain here is 0, then what we are talking about is h1 of x with coefficients in omega 1 closed. If you think about the definition, those of you who are familiar with this will see immediately that if you take L and you consider its first term class, and that gives you an element there. So this is it. So dl will be exactly the one that is produced by this construction. And to finish, I have like 5 minutes to go, and timing when it's quite convenient, I'll say just a few words about Bernstein valence in general on any manifold, CP1. CP1 for general n, I to an extent explained. How do you do a similar thing for a general simple liquid? Of course, you consider the flat manifold. So what? No, this is another time to talk about that. I should tell you another thing. So this is also worth the undertaking. I'll tell you something else. So, I said TDO, but I have never defined it. So now I'll tell you something that really will be generalized in the situation. So after all, what a TDO is, I talked about Picard-Lie algebra. What a TDO is. A short way to put it is, a TDO is a quantization of the Poisson algebra. It's a symmetric algebra of the algebra of fields. And I will explain exactly what I mean. So more explicitly, a TDO is a filter algebra like this, such that the corresponding graded object is isomorphic to this as a Poisson algebra. We've dealt with Picard-Lie algebroids. This is more or less the same as dealing with algebras of twisted differential operators. Here is why. So remember how we traveled from vector fields to differential operators. One way was formal, universal enveloping algebra stuff. And this carries over to the present situation without any changes. I'll write a definition and formulate the result, which, if you have time to think about, you will immediately figure out. So definition, so let L be the Chiral algebra on X. We know everything about such thing now. So what's U of L? It's like before, you can easily figure out. You take the universal enveloping. Well, I can't write it like this, unless symbolic. So it's U of L as a real algebra. It can be the answer. Remember, we discussed this. It is not just a Lie algebra, it also carries some multiplicative structure. But that has to be identified with multiplicative structure axiomatically coming from the universal enveloping algebra. So I have to quotient out obvious expression. So if you multiply two functions as elements of the universal enveloping algebra, you require that this be the same as their product natural. And likewise, f cross of tau. By tau, I mean an element of tau. But of course, if you split locally, that would be a vector field, and the result is independent. Actually, so whatever I think about it makes sense. Remember, there was one more element, the unit. There is an abstract unit coming from construction. It must be the same as the unit living in functions. So you quotient out by this ideal, and you get an algebra. So theorem exercise. UL is a TDO in fact. In fact, we have a function. So that gives us a function from L(x) to T. The over x that sends L to U of L. So this function is an equivalent of categories. Practical outputs. So, in one sense, what we've accomplished so far is we've solved the great problem of finding classifying all quantizations of this. All right, okay. Thank you.
Any questions? Any advertisement for the next lecture?
So next time I will move on to the